All right, welcome to video 4. This time we're going to be talking about a way to figure out rate laws. The last video we looked at figuring it out by inspection, and that works out okay with pretty basic types of problems. But I'm going to show you a way that works out all the time. And on the AP exam, I don't know if that'll happen this year if they give us a kinetics problem, but let's say they do. Something called the method of initial rates is math does the explaining for you. Instead of having to do what we did last video where we say, hey, if this doubles and this doubles, therefore the order is 1, the math does it for you. So let's jump to video 4 notes, if you guys can pull those out, please. And I'm going to go right now to I'll try a different color pen today because. So let's just pretend that we have two different rate expressions, right? And we have rate 1 and we have rate 2. One of the things that we can do is whenever we have, and let's say we had a table, right? And in that table we had a bunch of different rates. We had 1, 2, 3. And if you remember before, they had the concentrations were in the first two. So it'd be the concentration of A right here. And here we have the concentration of B. And then over here on the end, we have the rate. Right? So what we can do is we can compare any two rates, and we choose ones where one of the variables is held constant. So if, let's say we're going to compare experiment runs 2 and 1. If something happens between experiment 1 and 2 and B is held constant right here, right, then we compare what happens between the rate 1 and 2 as well. And typically the way we do that is we take whatever rate is higher and we divide the rate that's smaller by it. So I'm going to show you this, and then it's probably not going to make a whole ton of sense here until we actually do it on a problem. But let's say I did this. Okay, so what we do is we always take the higher of the two rates and we divide the smaller one by it. So in this case, let's pretend that rate 2 is a higher value than rate 1. So we'd write rate 2 is equal to K, the concentration of A1, that's the, I'm sorry, A2, because that's the second row, raised to its power, times the concentration of B2 raised to its power. And we're going to put all of that over rate 1, which is equal to K. And the same sort of thing, we're going to put A raised to the M, but this is the A from the first, and we're going to take our B and raise it to the N, and this is again for our first. Now, one of the things that we are delighted to do all the time is we love canceling out. So I'm going to cancel this out right now by doing this. I'm going to say my K is going to be the same in both cases, so that disappears. And if my B is constant, that means that the concentration here and here is the same. So that means that both of these things right here, they will get canceled out. And so if I rewrite it, ouch, my cat just jumped in my lap. If I rewrite this out, I'm going to end up with this. I'm going to end up with rate, that's going to go to this. It's going to be rate 2 is equal to K with only the A expression raised to the M. And all that's going to be over rate 1, which is going to be K A to the M, the first thing. Now, we can do the same exact thing with B as we just did right here, but it's kind of hard to visualize this just from scratch. So let's do a problem, because if we don't do a problem, this is not going to, as brilliant as I think what I just drew was, it's not going to be all that helpful to you. So we're going to actually do the math here, and I am not that neat, so I'm going to keep the mathematics that are done on my sheet here, although they did some canceling out in absentia. But let's take a look at this reaction right here, and I want to point out that the overall rate law of this reaction is going to be this. Rate is equal to K, and it's going to be ClO2, because that is a reactant. Remember, we only care about the reactants. That's a reactant raised to the M. We don't know what that M is. That's what we're going to figure out right now. And it's going to be multiplied by the concentration of OH minus raised to its order. So this is our base thing. Our whole goal in looking at this data right now is we want to figure out what these two variables right here are, the M and the N. Now, we're going to do this with the method of initial rates. And so what we have to do is we can pick one of these two reactions to start with, And the first one they want to start with, and we're going to work with right here, is they decided they wanted to go and they wanted to figure what the order was for ClO2. And remember, if you want to figure out the order of ClO2, you have to go over to OH and you have to find 2 runs where the concentration does not change. And by the way, do you see how they showed you the molarity was in molar? And let me remind you that molar isn't equal to moles per liter, because you may have to cancel those some units later. So if you take a look, what they did is they decided, hey, if you compare rate 3, so let's just make sure we have the numbers here. This is 1, this is 2, and this is 3. If you compare rate 3 with rate 1, the OH minus concentrations cancel each other out. Now let me remind you how this looks. So this is how you would do it from scratch. If you take a look, do you see how the rate 3 is 1.82 times 10 to the negative 2, and the rate 1 is 6.0 times 10 to the negative 4? This is bigger than this, which is why we put rate 3 on top of rate 1. By the way, all we're doing is comparing 2 runs. We could do it the opposite way, but no one likes working with decimals typically, so that's why we take the rate that's higher and put that on the top. So if we take a look at this right here, what we're actually would be doing, if I were writing this out, I would go rate 3 is equal to K times, and again, I'm just writing the values out. Wouldn't it be ClO2, the third run, right? All raised to the M times OH minus of the third run, and rate 1 would be equal to, and by the way, we're just going to divide these 2 by each other. Rate 1 would be, again, equal to K, but this time it'd be ClO2, still raised to the M, but this time it'd be the first run, and this would be OH minus raised to the N, but it'd be the first run. And what cancels out? Well, the K cancels out, and these entire expressions right here, they cancel out, which is why they give us this expression right here. Now I want you to pay attention here, because they actually plug these numbers in. So for this rate right here, they plugged in 1.82 times 10 to the negative 2, and that's what they got right here. And they divided that by 6.00 times 10 to the negative 4. So that's on this side. And then I want you to point out something here, and this is kind of a big deal. What's left over on this side, I'm just going to circle this, and because we don't have a lot of room, I'm going to just bring it over here. Do you realize if I have something like this, ClO2, right, and I have that raised to the M, and that's divided by ClO2 raised to the M, unless you think, well, they're the same thing. Well, remember, these are from different trial runs, so the numbers are going to be different right here. But if you have 2 things to the M, do you realize that we can simplify that just by writing ClO2, right, over ClO2, and this is, that's a really bad way of writing ClO2. This is, on the top is going to be the third run, on the bottom is going to be the first run, and this whole thing can be written to the mth power. So if you take a look, that's what they did over here, and they took 0.055, which they got from the table right here, and divided by 0.011, and when they set it up, they had 30.3 is equal to 55 to the m. Now, if you're good with logarithms and rearranging equations, you can just set this up and solve for m. It works, right? Or you could just think, what would I have to raise 5.5 to get to 30.3? And the answer for that is 2. So that means if we look back at our equation over here, we know that our ClO2 has to be raised to the 2 in our overall equation. Similar, we're going to do the exact same thing, but now we're going to compare, we want to figure out for OH minus. So this right here was for ClO2, trying to figure out its order. Now we want to figure out the order for OH minus, or we want to figure out the N more specifically. And if you take a look up here, do you see how between experiments 1 and 2, the ClO3 value doesn't change? And if you take a look here, doesn't the OH minus go from 0.03 to 0.075, and here it goes from 6 to 1.5? Kind of a big deal. So I'm not going to repeat all of what I just did there, but essentially what they did is they took rate 2, which had a higher value for the rate than rate 1. You could have done it the opposite way, and they put them on top of each other. And when they did that, they ended up with 2.5 equaling 2.5 raised to the n. Now, if you want to walk all the way through this, just let me remind you that what we did is we said rate 2 is equal to, and before we did anything, and this is important, we knew that the ClO2 was going to be held constant. So what they did in the problem is to make it simpler. They wrote a K in here, but everything that was held constant they got rid of. So the K was not included in here, but if we didn't know that, we'd write K OH, and then wouldn't we also still have the ClO2 in the problem? And the same thing would be on the bottoms, ditto, right? But the difference would be that it would be rate 1. And if we were canceling things out, the ClO2 would cancel completely, and so would the K. And that's why we end up with the expression right here the way it is. Now, if we have 2.5 is equal to 2.5 to the n, almost all of us would be okay with saying, oh yeah, we need to have a 1 in order to make those two things equal each other. So that means up here in our expression, although they do it right down below, we have OH minus be raised to the 1. And this is done much more neatly like this. Yeah? So that's version 1. Let's try a much more challenging problem. And this is almost worthy of another video itself. But I'm going to braze on. If you want to take a pause right now because your brain is sore, take a pause, then hit play again, and we'll keep on going. How about that? Yeah? So I'm going to give you one that is monstrous looking, and I'm going to kind of walk you through it, and I'm not going to do the math on the side because I actually did it on the paper beforehand here, which was a pain, by the way. But do you see how we have three reactants here? BrO3 minus, Br minus, and H plus. Again, we aren't going to worry about the coefficients right now. There's going to be a time where those coefficients are going to come into play and matter for us, but we could do it the old-fashioned way. But what we're doing always is whenever we want to compare, or we want to figure out the order of one of these things, and let me just put this over here in the top corner here. This is the rate law that we are trying to work out. We want to have rate is equal to K. We want to have BrO3 minus raised to the M times Br minus raised to the N all times H plus raised to the O. So we're looking for these three variables right here. Those are the important ones. And remember, if I want to get this M variable right now, it means I have to find two experimental runs where these two things are held constant. Same thing for the N. If I want to figure out N, I have to find a run where these two are held constant. Now, let's walk through this. So first things first, they chose that they wanted to figure out the order for Br minus. So this is for, let's take a look here. They wanted to compare rates 2 and 1 first. So we're actually figuring out BrO3 minus. I misspoke there. We want to figure out the order of BrO3 minus, right? And so if you take a look here, do you see how between experiment runs 2 and 1, see how this is held constant and this is held constant? So that means that whatever's happening here between these two is the only thing that's impacting our measured rate. And so what they actually did is they actually plugged these values in instead of writing the expression. So if you took rate 2 and just walked your way across rate 2, do you see how BrO3 minus is 0.2, like it is right here? The 0.1 is right here, and the 0.1 is right here for the H plus. Now they actually plugged the values in. If I was doing this on an AP exam, I would have actually written it out like this. I would have written rate is equal to, and I would have actually written out the BrO3 minus, my cat is actually pushing against the stylus because it's playing with it, to the M, etc., etc., etc. And then I would have gone to this step. But they just jumped the steps here. And if you see how, because the Br minus, which is this right here, and the H plus, which is this right here, are constant, they cancel out everything. And they cancel out the K. So in the end, what you end up with is 1.6 times 10 to the negative 3, which is rate 2, divided by 8.0 times 10 to the negative 4, that dot means times 10, and it ends up being 2 on this side is equal to 2 to the M power. And your M is equal to 1, which means that in our overall equation, we know right now that this M is 1. And that's going to be important. It means it's first order with respect to the BrO3. really quickly here. Again, we could have, if we wanted to, plug this into a calculator, but most of us understand that if we put something into this expression right here as a 1, yeah, it'll work. So then we wanted to work with BR. Now, if you take a look here, between experiments 3 and 1, do you see how 3 and 1, these are both held constant, and this is held constant, and this goes up, right? So we're going to do exactly the same thing with BR, and if you take a look here, we're just plugging in the numbers that we got from rates 3 and rate 2. And when we do that, you're going to see how, and I like the fact that they kept them in order. I kind of didn't do that on my first one. This is for BrO3 minus, this is for our BR minus, and this is for our H plus. And again, everything cancels out until all you have is this expression right here is equal to this expression right here. Again, let me remind you, if you have 0.2 on top of 0.1, oops, that's 0.1, and all of that is raised to and each of those is n, is the same as writing this. So this is the same as raising the entire thing to n. So when they do the math on this, again, you end up with 2 on one side and 2 on the other side, and your n value is equal to 1. So we say it's first order with respect to BR. And lastly, H plus, if we take a look at it, let's take a look at the actual expression up above. I'm going to use a different color here because I realize it's kind of getting all globbed in here. If you take a look here, we want to find where, you see how the only place where H plus increases is from here to here, right? But if you take a look here, or couldn't we do it from here to here or from here to here? In all three of these cases, either from experiment 1, 2, and 3, we could go to 0.2. Now, what's interesting I want to point out to you is that we could have done it with experiments 4 and 3 because didn't we already figure out what the orders were for these two things right here? So if we know the order for this, if we take a look in our equation, if we know the order for our M and we know for our P, then those are essentially constants. And I'll show you how we can do a problem like that. But what they chose to do, if you take a look here, they would decide to go between rates 4 and 1. I was going to do between 4 and 3 right now because I want to show you how 4 and 3 would work. And if you want to remind me in class, I can do that. But in fact, will you remind me in class to do show you how 4 and 3 would still have worked? But they decided to go between 1 and 4. So if you take a look between 1 and 4, it goes from 0.1 to 0.2. And here do you see that it's 0.1 and 0.1, and here it's 0.1 and 0.1. So essentially this is constant and this is constant, and it goes from 0.1 to 0.2. Again, we always like to put the higher order rate on top of the lower order rate, and so when we do that, we're going to end up with this. And the same exact stuff happens here. See how these units here cancel out? This cancels out. This cancels out, and the only thing that stays is this, and that's the same thing as writing 0.20 over 0.10, that didn't write very well, all to the P, right? And here what you end up, and it's interesting, and they said to heaven, they didn't care about significant figures. They said 4 is equal to 2 raised to the P, and that meant that your P value is 2. So they then put the values in for M, N, and O as 1, 1, and 2. Now again, you do not need to put 1 and 1 in here. Now, what I was just saying here, the changing between experiments 3 and 4, it said if there are not two experiments where the concentration of the reaction is different, but the concentrations of the other ones are constant, we can figure it out anyway, because by the last step, you will know what the other two orders are, so we can make them into constants. So let's just pretend, and this example right here, I'm going to change this, I'm going to erase this. Hopefully it doesn't confuse you, but let's say right here, let's say the values weren't, I'm going to make it in the black here. Let's say that this wasn't 0.1 and 0.2, right? Let's say instead this was 0.20 and this was 0.1, right? Well, watch. If I have 0.2 and 0.1, that's all raised to the 1, right? Well, isn't that 0.2 divided by 0.1? Isn't that just 2? So even though we can't cancel it out, we'd have the value 2 that we could multiply out, but we wouldn't have another variable we have to figure out. So as long as we know what the exponents are for each of the orders, we don't have to have those variables have the same, be constant once we've figured out what their orders are. Again, if that doesn't make very much sense, we'll work through it. The other thing is, this is like pretty close, 3.99 to the m, because that's really close to 4, and yeah. But I want to point out something to you here. They often, if you do a problem with this, they want you to find the rate constant. And so let's take a look here. I'm going to change my color pen again. What have we used here? Let's just use orange, this disturbing orange color. So that's solving for this value right here, this k. And here's how we do it. All we do is we pick any one experiment run, any one. Because all of the rate expression, this rate constant will be the same for every single experiment because the reaction that's being run is the same. And so they chose to pick the data in experiment 1. And if you're trying to verify this, let's look up back here in experiment 1, and the values they had here were 0.1, 0.1, and 0.1, and the overall value was 8.0 times 10 to the negative 4. So if we go back to this right here, what they did is they plugged in the 0.1 raised to the 1, the 0.1 raised to the 1, and the 0.1 raised to the 2, and they plugged in the 8.0 times 10 to the negative 4. When you do the math on that, and this is important, you end up with 8.0 liters cubed per moles cubed times seconds. This is all on the bottom. They will give you a point, if they give you a problem like this, they will give you a point for figuring out the units. Now, if you take a look at how is that possible, well, if you take a look, we have this. For our rate, don't we have moles per liter seconds? Agreed? And then on top of all of that, we have on the bottom, don't we have, this is molar times molar times molar, right? And molar squared, sorry. So that gives you molar to the 4th, right? Molar to the 4th is the same thing as moles per liter, right? All raised to the 4th. So if we wanted to, we could on the bottom, couldn't we write this? Because now we're going to have to divide this side over here. Wouldn't we have moles per liter all to the 4th? So we could write like this, to the 4th. And if you want to do some canceling out of units, right, the other thing you can do is you can take this entire expression and you can flip it over here and multiply it. And when you end up doing that, this reacting with this gives you liters cubed per moles to the 3rd times seconds. If we need to, we can go over that in class. Hopefully this has been helpful. It's a really long video. I'm going to cut it off right here. See you in class.